Hello everybody, Miss Denton here again, and in this video we're looking at squares. Now I hope you're getting the pattern to what we're doing. Each shape we study, we measure the shape, we find the truths about the shape, and then we apply them with our SOL practice problems. The further along we get, the more properties each shape has, and here we are at a square. Now, your head might be spinning with properties because you're on your fourth shape of the series. However, don't overthink a square, guys. You know everything about a square already. Just stop and think for a second about what you know about a square. You know that a square has 4 equal sides. And you know that a square has 4 right angles. So let's start there. Let's start with the things you know. If you know that a square has 4 right angles, you know each of these angle measures is 90 degrees. If you know that a square has 4 equal sides, then all you need to do is take your ruler and measure one of the sides, and then you'll know how long all 4 are. And I'm getting, depends on where I move my ruler to, it's kind of right smack dab in the middle between the 6.1 and 6.2. So I think I'll go with 6.2. Let's go with 6.2. Obviously, we're doing a little bit of rounding here. So if this piece is 6.2, then all 4 side measures are 6.2 because you already know that a square has 4 equal sides. Okay. Now, let's take on this diagonal work again. Diagonal from A to C. You could measure it. You can do that. I'm going to go ahead and measure it, and then we're going to see how accurate that was. I'm getting a measure of like 8.9. 8.9. And I think I might write that in pencil. Okay, I might write that in pencil because I want to do a little bit of math work to make sure that that's an accurate answer. Now, what kind of math work might I be talking about? Well, here we are again. Here we go. Right angles mean that there are right triangles, and right triangles mean that I'm going to be able to use Pythagorean theorem. A squared plus B squared equals C squared. The A and B are both 6.2. So I'm going to pause the video, take a moment, and solve for C. All right, how'd you do? Here's my work over here, 6.2 and 6.2. Square them, add them, take the square root to solve, and I get 8.8. So my measure was just a smidge off. It was 1/10 of a centimeter off. That is not too shabby. So instead of 8.9, I should have been measuring at 8.8, which means my ruler shouldn't have been here. Gosh, corner to complete corner, I should have moved it in just a smidge. 1/10 of a centimeter is not much, but I'm going to go with 8.8 because I know that I use the Pythagorean theorem, which is more accurate than my ruler, assuming that these are accurate. All right, what do you think about BD? Maybe even without doing any math, without measuring, can you just eyeball it? Think about a square. It's super symmetric. So if the distance from A to C is that 8.8, the distance from D to B is exactly the same, another 8.8 centimeters. There's lots of math to support that. We could throw in some lines of symmetry. We could redo the Pythagorean theorem. We could plop out our ruler and remeasure it. But these two diagonals are congruent to each other. Now let's talk about the parts of the diagonal. E has all along been a midpoint. It still is. E is a midpoint. And it looks like a midpoint. That's what I mean by don't overanalyze. E looks like it is in the middle, and it absolutely is in the middle. So if my entire length from A to C is 8.8, it should make sense that if I cut 8.8 in half, I land at 4.4. 8.8 divided by 2 is 4.4. So each of these pieces is 4.4 centimeters. All right, so maybe you're thinking, I've seen that before. I have seen where all 4 pieces of the diagonals are equal to each other. Well, let's look at our shapes over here. It was not in the parallelogram. The parallelogram is slanted, and because it's slanted, it forces one diagonal to be short and the other to be long. So that's out. It was not in the rhombus. The rhombus is very similar to the parallelogram in that one diagonal is short, I have 8 centimeters here, and the other diagonal is long, 10.4. Okay, so that just leaves us one more shape, and that's the rectangle. Check it out. The rectangle, which also stands at all 90-degree angles, has a midpoint that slices all 4 diagonals into 4 congruent pieces. It's these vertical and horizontal lines of symmetry that pop up, and it comes from the angles being 90 degrees. So this square is like a rectangle that's been squished in, and all 4 90 degrees still make those lines of symmetry we talked about. And it creates 4 equal pieces to the diagonal. All right, what's next here? I think we've got all of our side measures. Let's move on to these angles. We always start at the midpoint E. All right, so let me get my protractor set. On E, working on this upper angle. And what do we notice here? I'm going to get my ruler out. My diagonals aren't quite long enough. Line everything up. I'm headed for another perfect 90-degree angle. Check that out. So the midpoint E is also a perpendicular bisector. This is a perfect 90-degree angle here at E. Well, use your vertical angles. That means all 4 angles around E, where the vertex is E, these are all the vertices. The vertex is E of each of these 4 shapes at the top line. They're all 90 degrees. Now you might be thinking, that's familiar too. I've seen that before. I've practiced that. Yes, you have. Check out this rhombus. A rhombus is also 4 right angles that surround E. So we're squishing shapes together. You guys, I want you to think of a square as kind of the marriage of a rhombus and a rectangle. If you put the properties of a rectangle together, combined with the properties of a rhombus together, you end up with a square. The rectangles have those 90-degree angles. They have the congruent pieces here at the diagonals. A rhombus has that 90-degree perpendicular intersection in the middle. A rhombus has 4 sides that are congruent to each other. So a square is really the combination of a rectangle and a rhombus. Let's keep going. Something else super cool is about to happen. Okay, angle EAB. EAB. Look in here. Line everything up. I'll do it upside down. There we go. EAB. If you're having trouble with the protractor, come see me. Be happy to help you. Check this out. EAB. Cutting through here. definitely an acute angle, so I'm going to count from the outside this time. 0, 10, 20, 30, 40, and exactly, boom, exactly halfway, 45 degrees. This is about to get super easy. If I'm thinking of complementary angles, and this one's 45, then this one has to be 45, because 45 plus 45 makes 90. That's EAD. And if I'm thinking about alternate interiors, then these two 45s would transfer down here to another set of 45 and 45s. That's ECB and ECD. And if I'm thinking about those lines of symmetry, like the rectangle has, draw that in. If I'm thinking about those lines of symmetry, then anything that's on the top can flip to the bottom, and anything that's on the bottom can flip to the top. So these two 45s in the top left corner are going to flip down to the bottom right, to the bottom left corner. And these two 45s are going to flip up here. So every single angle in this picture is either a 45-degree angle or a 90-degree angle. And that is the power of the square. The square is so symmetric. In fact, how many lines of symmetry are in this square? Think about that a second. We can fold the square top to bottom, left to right. We can also fold the square along the diagonals for a total of 4 lines of symmetry. Other cool things about the square. Hold on, there's more cool things. Let's just highlight one of these triangles. Yeah, I've got my 90-degree angle here to build a right triangle. I also have a 90-degree angle here to build a right triangle. 90 and two 45s. Well, that's isosceles, and sure enough, we have an isosceles set of lines, 4.4, 4.4. So if we have two sides that are equal, we have two angles that are equal. Oh my gosh, a square is a geometry teacher's nerdy dream. Man, oh man, there's so much I could teach you here. The good thing for students is there's not a lot of guesswork to a square. You should really be able to eyeball a lot about a square. If you're given a measurement, you can work with that measurement within the constrictions that you know, the Pythagorean theorem or lines of symmetry. We could have even worked on some right triangle trig here to find anything that's missing. Let's highlight its characteristics. A square. Got something to look at. All right. Both pairs of opposite sides are parallel. Yes, indeed. Not just one pair, both pair. Both pair of opposite sides are congruent. Yes, indeed. In fact, all 4 sides are congruent. Both pair of opposite angles congruent. 90s, 90s. That's a yes. Not only one pair, but all 4 pair. Diagonals are congruent to each other. 8.8, 8.8, that's a yes. Diagonals bisect each other. 4.4, 4.4, that's a yes. Diagonals are perpendicular. There's your 90-degree angle in the middle. That's a yes. Diagonals bisect the angles in the figure. It took this 90-degree and split it in half to two 45s. That's a yes. Ooh, lots going on here about a square. Now, I'll make sure you get this. This is super cool. We have been on this journey of all these shapes. I'm going back to our original, which was a parallelogram. The parallelogram had the fewest characteristics. Pairs of opposite sides that are parallel and congruent, opposite angles congruent, diagonals bisect each other. So these 4 characteristics come from the parallelogram. Parallelogram. The next shape we looked at was a rhombus. The rhombus had the 4 properties of the parallelogram, and it added, gosh, why am I keeping an R there? And it added in 2 more properties for the rhombus. I'm going to put RH for rhombus. And those 2 properties are here. The diagonals are perpendicular. The diagonals bisect the angles. The next shape we studied was a rectangle, which had the 4 shapes of the parallelogram, or 4 properties of the parallelogram, plus these 2. All 4 angles are congruent for the rectangle, and diagonals are congruent for the rectangle, which are these 2. So the square, all the properties of a square actually come from other shapes, which means a square is a rhombus, a square is a rectangle, and a square is a parallelogram. It's so specific that it can fall into any of those categories. So cool, so cool, so cool, so cool. All right, let's do a little practice. Given that this square ABCD, given that this is a square, what's the length of AD? Okay, so we know that a square, from way back from when we were kids, little kids, we knew that a square had 4 equal sides. Therefore, the algebra that goes with this concept is 3x minus 5 is equal to x plus 1. Take a moment and solve for x. Okay, you can check out my work. I got x equals 3, but I'm not circling that. Go back to the question. What's the length of AD? AD. So we got to plug in. 3 times 3 minus 5. 3 times 3 is 9. 9 take away 5 is 4. So the length of AD is 4. Next example. ABCD and ECFD are both squares. All right, let's find those. ABCD here and ECFD here. Okay, they're both squares. From A to C is 28 millimeters. Now, A to C is a full diagonal of the yellow square. Okay, what is the perimeter of the pink square DECF? What is the perimeter of this square? All right, so this 28 millimeters goes with the yellow square. Somehow we have to transfer over to the pink square. All right, so think it through with me. A to C, the full diagonal is 28. What do you know about point E that could work on that 28? From A all the way to C is 28. Well, E is a midpoint. It's a midpoint. Can't stress that enough. So if E is a midpoint, we can take that 28 and break it in half into 14 and 14. Now, let's go over to the pink square. We also know that all 4 sides of a square are equal to each other. So this 14 is the same measure for each side of the pink square. So the perimeter is going to be 14 plus 14 plus 14 plus 14, which is, 4 plus 4 plus 4 plus 4, that's 16. 1, 2, 3, 4, 5, 56 millimeters. All right, one final practice for us here, and this is not a problem-solving question. This is going back to the properties. Select each property that's valid about the diagonals of a square. So if you need to have a visual, draw the best square you can draw. I know it's probably hard to draw a perfect square. Draw the best square you can draw. We're being asked about the diagonals, so draw in the diagonals. And let's answer these questions to the best of our ability. The diagonals are perpendicular, which means they intersect at 90 degrees. Yes, they do. The diagonals bisect each other, which means that this point right here is a midpoint. Yes, it is. Bisect means to cut in half. The diagonals are congruent to each other, which means from corner to corner is equal. Yes, it is. If they're perpendicular, those are opposites, not perpendicular, so we're not picking that. Bisect and do not bisect, those are opposites, not picking that. Congruent and not congruent, those are opposites, so not picking that. Whew, okay. That was our fourth main shape of the series. Practice, practice. Come talk to me if you need to, and happy studying.